Financial Maths, Geometric Series Type 6 Mortgages and Loans. So this is the second video for our mortgages and loans, and this is based on our method 2 approach, which is the amortisation formula. So this formula is generally only used for loans and for mortgages. It becomes a bit more complicated if you go to use it for a savings question. So my advice is never to use it for anything other than loans and mortgages. So the formula itself can be found in our maths tables, page 31. And the formula is that the amount of the repayment is going to be the mortgage or the loan drawn down times the interest rate times 1 plus the interest rate to the power of t all over 1 plus I to the power of t minus 1. So we say A is our repayment amount, P is our value of the loan or the mortgage that is drawn down, I is the interest rate in decimal, and T is our time, in other words, the number of compounding periods. But there's a couple of clauses with this formula. The most important being that this formula assumes the payments are made at the end of each accounting period. So unless stated otherwise in the question, then there's no issue. But sometimes, rarely, it'll actually say that the repayment is made at the start of the accounting period. And if that happens, you cannot, under any circumstances, use this formula. Instead, you would have to use the geometric series. If you were using it for a savings, you'd have to end up working with getting the present value and discounting back. So it becomes too messy, as I said. So stick with it for mortgages and loans only. So we're going to repeat the same example we did in the previous video, but this time we're just going to use the formula. So we had a couple buys a house and needs to borrow a mortgage of 270,000. It's over a period of 30 years. They get a fixed rate mortgage of 4.25% per annum. The bank requires them, however, to pay the mortgage back in equal monthly instalments. And then what is the monthly repayment? So what we have to do is look at our formula. And we know that in the formula we have P, it's our mortgage value, I is our interest rate, and T is our time. So does our time match our interest rate? And it doesn't, because we want months and the interest rate is per annum. So therefore the first thing we always have to do is check our rate and therefore change the rate. So we're going to change the rate from yearly to monthly. So we have F is equal to, P I should say, is equal to 100%, in other words 1. F is going to be 100% plus our 4.25%. So that's going to be 1.0425. And then our time, well, there are 12 months in a year. That's going to be 12. So therefore we'll have F is equal to P by 1 plus I to the power of T. So summing in our values, we have 1.0425 is equal to 1 by 1 plus I to the power of 12. If I get the 12th root of both sides, and then get I on its own, then that gives us an interest rate for the month, and I'll keep it to 4 significant figures, so 3,474. So now we know what I is, we can sub into our formula, because P is our mortgage amount, so 270,000. I is our interest rate, which is 0.03474, and that's monthly. Our time is 30 years, but we have to change that to months because the repayments are monthly. So therefore that's going to be 360, and we're looking for A. So we know that A is equal to P times I times 1 plus I to the power of T all over 1 plus I to the power of t minus 1. So subbing in our values, we have 270,000 times 0.003474 times 1.003474 to the power of 360 all over 1.003474 to the power of 360 minus 1. So a lot quicker than setting up a geometric series, and no hassles with kind of that power of 1 or power of 0, but that's because we're assuming our payments are made at the end of the accounting month, unless told otherwise, in which case we cannot use this formula. So that gives us a value of €1,315.43. So it ends up being exactly the same as what we got with our geometric series. So you're going to do the following questions then in your book, so page 264. And you're going to do question 5 and 14. And be careful with question 14 because you're looking for how much have they left to pay, okay? Now I'm going to show you where this formula has come from. So this is your proof for the formula. And then you can start those questions. So we start by saying, well, we want to prove that A is equal to P by I by 1 plus I to the power of t all over 1 plus I to the power of t minus 1. So before we start the proof, we need to make a note that the sum of the present values of each repayment over a given period of time has to equal the total value of the mortgage. So in other words, our present value would be given by the amount divided by 1 plus I to the power of t for each repayment made, and then that would be set up as a geometric series, where P is our mortgage value, A is the amount of the repayment, I is the interest rate in decimal, and T is our time, so our compounding periods. But of course, we have to assume for these questions that it is at the end of each accounting period that the repayments are made. So therefore, it becomes straightforward to set up our proof, because all we need to do is set up our mortgage as a series of present values of our future repayments. So the first repayment made at the end of the first accounting period would have to be discounted back by 1, whatever the repayment time is, whether be it monthly, weekly, fortnightly, biannually, or yearly. But because it's made at the end of the accounting period, we have to discount it back to the day the mortgage is drawn down. The second amount of the repayment would have to be discounted back by 2 periods, and the next one would have to be discounted back by 3 periods, all the way until we get to the last one, which would be discounted back by the total number of compounding periods that there is. So now all we need to do is see this as our geometric series. So I'm going to take out A as being common, as we always do, just to make it a little bit easier. And that gives me 1 over 1 plus I plus 1 over 1 plus I squared, all the way down till we get 1 over 1 plus I to the power of t. So now I see this is my geometric series. And I say, well, A is 1 over 1 plus I, or is also 1 over 1 plus I, which means that that's less than 1. And therefore I can get the sum to n terms. Page 22 in my maths tables. And n is the number of compounding periods. So in this case, that's obviously just t. So I then sub into my formula. So I'm going to have S of n, which would be the sum to t terms, is going to be 1 over 1 plus I times 1 minus 1 over 1 plus I to the power of t. And that's all over 1 minus 1 over 1 plus I. So to get rid of my fractions here, I'm going to multiply the top by 1 plus I, and therefore the bottom by 1 plus I. So I'm not changing the value overall. So if I multiply the top line there by 1 plus I get 1 plus I over 1 plus I, which is just 1. And then that's 1 minus 1 over 1 plus I. And that can be written as 1 over 1 plus I to the power of t. And then if I multiply the bottom by 1 plus I get 1 plus I minus 1. Okay, so now what I'm going to do is I'm going to multiply the top and the bottom by 1 plus I to the power of t to get rid of the fraction. So that gives me 1 plus I to the power of t minus 1 all over I times 1 plus I to the power of t. So that's my geometric series. That's the sum to n terms, or the sum to t terms there. And all of that has to be multiplied by a. So in other words, we have p is equal to a times 1 plus I to the power of t minus 1 all over I times 1 plus I to the power of t. So now I'm looking for a, so all I need to do is rearrange my equation. So I'll multiply both sides across by I by 1 plus I to the power of t, and divide across by 1 plus I to the power of t minus 1. And now we can work out our repayment amount.